Hi you guys, this video is a review or an overview of the topics that we didn't get to in class today. So the remaining concepts that we want to make sure we know when it comes to our definition of continuity and how that ties into what we know about limits and how we work with limits. So these three functions that we're going to check out, and these are on the slides that you have from the website too, are functions where it's a little bit less intuitive right away what's going on. So these are kind of special cases of continuity analysis. They're ones I want you to be able to recognize, and there are a couple of things that I want to draw your attention to make that recognition easy. So the first function that I would like to have you take a look at is that cosecant of x. And this is really going to be true for any of your reciprocal trig functions and your tangent function as well. So for cosecant of x, if we think about this function, it's easier to think about it if we rewrite it in terms of sine. The same would be true for secant in terms of cosine. The reason that we want to do that is because at this point we can easily identify where we're going to encounter issues with continuity. And that's going to be any place that sine of x would be equal to 0. Because anywhere sine of x is equal to 0, I would be trying to divide by 0, which is problematic in this case. So when sine of x is equal to 0, that occurs anywhere where x is going to be a 0, a pi, or a 2 pi. So over the interval of x values from negative infinity to positive infinity, we are going to have discontinuities for cosecant anywhere x equals pi times some n value where n is an integer. And, oops, I just fast forwarded my slide. So that's the same approach I would take again to secant, to tangent, to cotangent as far as the description of continuity. The next two that I want to take a look at also happen to involve trig functions, but they're going to involve trig functions in a really different way. Let's analyze this first piecewise function here for option B. What we have is a function that is one piece at every single value except for 1. And that one place where it's not the original function is at the point of the 0. So first let's consider the main function, the one that this piecewise is as long as it's not at 0. This function, we don't have any issues with it unless we're trying to divide by 0. So this function is going to be continuous everywhere but x equals 0. Everywhere but x equals 0. So that means in order to figure out the continuity of the entire piecewise function over here, we need to know what's going on at the other point in time. So it's not defined as this function at 0, but instead it's defined as 1. So with this function, anywhere it's not 0, it's continuous. At 0, I have a defined point. So then I need to think about limits when it comes to identifying, am I going to be continuous over my entire interval from negative infinity to positive infinity? And so here I want to analyze limits. Everywhere except for 0, I have the function sine of 1 over x. So I need to know what is the limit as that function approaches 0. When we have a sine or a cosine and one divided by a variable, what we have is the oscillatory issue. So we talked about limits that don't exist. This is one of those because of the oscillations. And the shape that we saw is something that looks like this right around 0. So because this limit does not exist, even though I have a point defined at 0 as 1, I still have a discontinuity there. Because remember, your conditions for continuity are that f of c is defined. So at a specific point, you have a defined value, and we've got that there. The next issue, though, is that the limit as x approaches some value, in this case 0, oops, I hit ahead twice. The limit as x approaches c of our function, that needs to exist, and that's where we have an issue here. Sorry, you guys, my hand keeps bumping the go forward slide. So we can't have continuity when the limit as we approach that value of 0 does not exist. So this piecewise function in part B, the limit does not exist, so we have a discontinuity, which I'm going to abbreviate as disc, at x is equal to 0. So that's our issue here. Now we have a couple of things that we want to do when we are comparing example B to example C. So notice that a lot of these things look really similar. I've got a function where there's a trig function and I'm trying to divide by a variable. It's only at 0 that I need to be concerned. But as I go through the 3 conditions for continuity, I'm going to see that things look a little bit different. So with this function here, I have the sine of 1 over x, which is what I had in the previous example B as well. But I have that function x out in front. And this draws us back to what we talked about today with Squeeze Theorem. If I just have this component here, then I have the oscillations. And if I have oscillations when I'm trying to divide by 0, I don't have a limit because I'm going back and forth infinitely many times. When I have that x value out in front, the x value means that all of a sudden I have an option for identifying a limit, because then I can check things out using the Squeeze Theorem. So recall that with the Squeeze Theorem, if I talk about the function sine of 1 over x, the oscillatory function, because it's a sine value and there's no change in amplitude, this function always exists between the values of -1 and 1. So if I were to multiply all pieces of this equation by x, then all of a sudden I have the original function that I'm interested in part C. And it exists between -x and x. So if I take the limit of each of these expressions, if the limits in my outer bound are the same, then by the Squeeze Theorem, because this sits between those values, I'm guaranteed to have the same limit that I end up with at the end. So let's check those out. If I take my limit here, as x approaches 0, of -x, I'm really sorry about that, I'm going to end up with 0. If I take the limit as x approaches 0 of x on the other side, I'm also going to get 0. So this limit is 0 as I approach 0. The reason I'm interested in what's going on as I approach 0 is, again, the break in the function is occurring at 0. Now, I need to check, do my 3 conditions exist here? Are they all being met? The first one is, do I have a defined function value at the point where I would have concerns about discontinuity? And I do. At 0, my function is defined. So my first condition is met. The second thing is, as my function approaches 0, the point where I'm concerned about the discontinuity, do I have a limit that exists? And I do, right? There's no issue here because I can prove the existence of the limit with that Squeeze Theorem. Last up, I need to check that the limit that exists is the same as the value of the function. And 0 is the same thing as the 0 here, so I am good to go. So this function does not have any discontinuities. Over its entire interval, it meets all of the conditions that we need for a continuous function. So we are good to go with this one. So notice the main difference here was the presence of an x in front of the trig function, and then the fact that this value was equal to the limit that we were working with. All right, you guys, that's mostly it when it comes to limits and continuity. There's one more theorem that is introduced in this section that you want to be aware of. And the reason we want to know about this function is it just is a good guarantee of certain information so that as graphs has some strange characteristics, we still know that certain values are occurring over a closed interval. And so the theorem that we're going to talk about next is called the intermediate value theorem. So let's see what it says. If f is continuous on the closed interval a to b, where f of a is not equal to f of b, and k is any number between f of a and f of b, then there is at least one number c on the interval such that f of c is equal to k. So let's think about this in terms of numbers. If I give you a closed interval, so let's say our closed interval is -5 to 7, and f of negative 5 is not the same thing as negative 7. So my y values are not the same as those two x values. Those x values don't produce the same two y values. And then k is some number in between f of a and f of b. Then we need at least one number in between where we have an output value of that k. So if you think about negative 5 to 7, and I'm going to put my negative 5 over here and my 7 over here. So let's say that this is my closed interval. And then let's say that f of negative 5 is negative 6, and f of 7 is equal to 10. So what I have is a point down here at negative 6 and a point somewhere up here at 10. So not quite to scale. So what I know is if I have a closed function, somehow if this will not cause me to pick up my pencil at any point, no matter what happens in between negative 6 and 10, I somehow have to meet every single value of numbers that exists in between those two y values, in between negative 6 and 10. So if k is a number on that closed interval, like let's say 5, because negative 6 is in between, because 5 is in between negative 6 and 10, there's no way to get from down here to up here without passing through 5 at least once. Which seems a little bit obvious, but that's not necessarily true if my function wasn't continuous. If it weren't continuous, I could have a jump in the function, or I could have an asymptote that might prevent me from ever actually touching the value of interest. So if you have a closed interval, and on that closed interval you're going over a series of y values, if the series of y values contain a number that you're interested in, you know it has to pass through that number at least once. So let's check out two examples of what that looks like in more depth. The first one is an example here. We have a function, it's a quadratic, and we want to see, are we guaranteed a 0 on that interval? So let's go ahead and give ourselves a graph here. So if I'm giving myself a graph, I have a quadratic, and I'm interested in what's happening from the interval of negative 5 to 0. So I need the corresponding y values for this function. I know the y-intercept is going to be 7, because if I plug 0 into that function, I am going to get out 7. So I've got a point there. Then I also want to figure out what's the y value if I plug in negative 5. So when I plug in negative 5, the value that I get out on the other end is going to be negative 28. So I'm down here somewhere. So in order for a continuous function to get from negative 28 to 7, no matter what happens in between, it has to pass through all of the y values. So my y is going to fall, all of my y values are going to be in between these two numbers, and I'm going to meet every single value in between, because there's an infinite number of points going from negative 28 to 7. So because it has to pass through all of the values, there is definitely going to be at least one 0, because I can't get from negative 28 up to 7 without passing through 0. That's what the intermediate value theorem tells us. Let's check out one example of an intermediate value theorem problem on the AP Calculus exam. So here's a multiple choice problem. It says, let f be a continuous function on the interval negative 3 to 6. So once more, I'm going to give myself a graph, and I'm going to go from negative 3 up to positive 6. F of negative 3, it tells me, is negative 1. F of 6 is 3. So no matter what's happening in between here, I have to get values that go from negative 1 up to positive 3. So then I want to check out my solutions. I don't have any way of guaranteeing a specific point, so I don't know that f of 0 is 0. Part B is asking me about a derivative. We don't know about derivatives yet. It's not going to be that solution. So then I want to see, is my function always between negative 1 and 3, in between negative 3 and 6? Well, no, because it could go outside of those values. Like I could have my y values come down here and then go up here and return. So it can go outside of those. It says my function value is going to be y for at least 1 for at least one point between -3 and 6. And that's true because if I'm going from a y value of -3 up to 6, it has to meet